Let's go, Stella.
Oh, okay. Oh, I thought you were doing this. Okay, cool. So, hi, welcome to the 13th session of Visual Learner Study Club. Just be aware we are recording this session, right? It's going to be hosted on the YouTube channel, so you should be feeling comfortable what you do and what you say here. Also, we have kind of a tight agenda today. So some of you know that last time we were going, thanks to Roro, through some Python stuff to catch everyone up who is already entering Module 4. But now we are going back to actually finishing Module 3. And we're going to talk a little bit about calculus. And just talking about myself, I haven't touched calculus in 20 years. Uh, so for me, it's quite some catching up to do, to be honest, and I really appreciate Roro giving us some insights. I also had the pleasure of being able to do a quick session this week with Octopus because I really didn't understand how he came to the resolve of one of the equations that were in the course. So we're going to talk about that today as well. First things first, I wanted to say, because we have, can you go to the next slide? Okay, so because we have one new person in the study group, Artem, please, can you introduce yourself quickly?
Sure. Yeah, my name is Artem. I'm from Russia. Actually, I joined this Token Engineer Academy since the course was launched. I finished four modules. But a little bit about myself. So I'm professional petroleum engineer. I'm far away from software and IT stuff. So, and like during COVID time, I decided to switch to crypto worlds and Web3 and blockchain. So I started to learn myself, doing some boot camps and courses online. And yeah, I'm contribute to Odyssey DAO, one of the core contributor. We are doing very simple, actually try to onboard people and explain Web3 as for and very plain language. So I'm contribute there. So very happy to be here. Good.
We're happy to have you.
Yeah.
Kojak, you wanted to add something to that?
No, I was just checking my voice.
Oh, okay. Cool.
Okay. Yeah,
so,
sure.
Yeah.
Then, next slide. Okay, so I had this request in the group actually from Lakshman. Now Lakshman is not here, so I'm kind of, I think we should go through the points. He has stated that he has a lot of trouble finishing the exam for Module 1, which, you know, is totally fine because there was a lot of reading that we had to do.
Sorry, are you recording? Because I'm not recording.
Yeah, of course I'm recording.
Okay, good.
Come on,
Good.
I'm a
Sorry.
reliable person. Yeah. I'm recording. Okay, so anyhow, I just wanted to share some best practice and I was hoping that you guys also have some best practice for taking on the exam, specifically Module 1, because it actually has a very specific approach to the exam questions. So one thing we found out when Rohan and I were going through the first module is it's not really about our opinion, is it? It is about grasping what is the opinion of the authors of these different texts or articles that we had to read or papers. So going through the questions not by answering it like, oh, this is what I think about it, but rather like this is the interpretation that was given to me by the authors would be probably helping a lot in answering the exam questions. Then another part is obviously Florent provided us with the question sheet, which is like really good to prepare for the exam and also to link up with other people who are taking the same exam right now and confirming with them if they think the same. So you can kind of discuss your answers with each other. That's an option. Obviously, check our recorded sessions. That's what they are for, right? Because in the sessions we went through, specifically in Module 1, we went through all the questions, which we haven't been doing for the other ones. Now that we have theoretically the question sheets again, we could do that. To know which session had what kind of content, you can check our Notion page because Rohan was as nice as writing little summaries for every session, which is truly amazing. Thank you for that. And yeah, I don't know if any of you, I just realized Artem has already gone up to module 4, and I know some in here are in module 2 or 3. I don't know, do you have any recommendations to share with Lakshman on what's your best practice, or what was your best practice to approach exam in module 1?
Yeah, maybe I can share my experience. So yeah, I found model 1 is a little bit different from rest, as you pointed out that yeah, sometimes it's not our opinion, but what was in the paper. And actually, what I also a little bit struggling. I need several attempts to pass this. So what I did actually, sometimes I just try to search, for example, some keywords from question into this paper, which they reference, and then read this more carefully, this maybe a paragraph or two, and then answer again. That helps me. So it's just because sometimes it looks like answer is exact wording in this paper. This difficult. It's not like a rephrase or they're looking for exact as it was in paper. So this helped me to pass.
Thank you. Yeah, exactly my point. Strata, Hibiscus cultivar, Kojak. Any additions? Lutra? Oh, Strata is coming in with his face.
Well,
he's beaming in.
Thanks. The thing I just say to Lakshman is make sure you understand. Like it's not about passing the exam. It's about understanding the content. And when you can understand that content, you can really answer those questions. So like sometimes I go over some content multiple times just to make sure I fully, thoroughly understand it. And so I think in this world of, not enough time and so much to do, I think if we can, take the time to fully understand, I think that'd be, and then, whatever other people will say, I think is all valid. But I think it's really about understanding the content. That's my 2 cents. Well,
wait, Lutra, did you just confirm?
Yes, I wanted to, but I had some difficulties with my mic, but I hope that's fixed now. I find it helpful to have the text by my side, just to have a brief look up, and it's really more about getting the content, as Strata already said, and then I think you will be able to solve the questions of Module 1.
Yeah, I also think you guys are right in the sense of rereading some of the things. Especially I just realized, like, some of us, right, we are not native English speakers. So the way those articles are being written is kind of like very high level English. And so that's something that even gave me sometimes some trouble, where I was like, oh, damn, I need to read this again. Like, I probably would have understood this in German, but I really didn't understand this in English. And I think that's totally fair, right? We're trying to do this with not being native speakers on many occasions, which is an additional hindrance. Hibiscus cultivar.
Yeah, so the very simple advice I have is to echo what everybody already said, but simply put, the TLDR of it all is don't do TLDR. Read slowly, carefully, and it becomes a joy of reading these texts, and that's how you pass it.
So good. Yeah, patience is probably key. I agree. Okay, cool. Let's move on, because now it becomes really exciting. This is something I really didn't understand. I was like, wait, 6-dimensional math? What the hell? I only knew about 3 dimensions and maybe a 4th one. And and then I understood further what this actually means. But I guess I give it over to Rohan to fully explain. And welcome to the middle of Module 3.
Yeah, so I mean, there are many things in all of these modules that we've covered. There are many even like the way Michael speaks about things a lot of times in the papers, you hear the terms like spaces, like, the state space, or what is a state itself, right? Like, or you have dimensions, and the calculus is thrown around left, right, center with, like, derivatives, and maybe not integrals, with partial differential equations. Differential equations is probably a term you might have heard here. But like in all of these things, what you need to realize is these concepts aren't that difficult, and the amount we need to understand isn't much. Like you can just, it's not, when someone says, hey, we're using calculus in this field, it's not like we have, I mean, for the most part, right? It's not that we need to understand everything about vector calculus, or we need to even know how to differentiate like use partial differential equations. We don't need all of these things, but knowing them will help reading white papers will help you at least get a grasp of what is being spoken about, and you can use other tools to actually go deeper. If you want to do a differentiation, there are many tools online that can help you do it, but the first task for us is to understand what these words mean and why they're used in these contexts. So first thing we saw in module 3 that we thought was very mathy was something like this. This basically in some sense is a this is a statement you'll read a lot of times. In general, like what I want to say is, when someone says that we're talking about a 6-dimensional number, or a vector, or like any kind of item, these dimensions for us basically just mean something along the lines of, like, for example, where it comes from what I understand is like, if me and Stella want to meet, right, and we decide, hey, like we're going to meet sometime next month, there are a couple of things that I'll need to know from her end or from my end to be sure that we're going to meet. One is time, like when are we going to meet? Second is the space, like in the sense that where, so where and when, right? Those two things can cover everything. But when includes like 3 dimensions of space. Like for us, it's practically 2, because it's like the latitude and longitude. Like where on the map do you want to meet, and what time do we want to meet? Those 2 things can actually cover all the information that I need in order to meet you. And so that is a 3-dimensional information, like 1 dimension of time, right? And 2 dimensions of space, x and y coordinates on a map. That's a 3-dimensional state that we're talking about. If you look at, for example, I think I'm sharing my screen, so I should be able to do this. How do I go back from here? F11, yeah. So like, we solved the farmer's Python thing, right, last time. If we go into the state we defined here, right, this was our state that we called it. Here, if I ask you, like, how much information do I need in order to define the state, right? Basically, we need, like, for example, if I want to know everything about a person, if I want to know everything about a store, I need 3 sets of information. How many apples they have, how many bananas they have, how much money they have. That's a 3-dimensional item. And this you could call a vector. Simply because, like, it's 3, you could map this, right? Like in the sense that just how XY is a coordinate system, and on a map, when you put a point, it's like you can make a map out of it. So every point will represent a different XY, a state space of like different XY points. And every XY point will be a different location on the map. Same way, like we could make a like graph of apples, bananas, and money, which is a 3-dimensional map. If we just do apples and bananas, it's a 2-dimensional map, where I just need an X and Y coordinate. If I need an X, Y, and Z coordinate, then it becomes a 3-dimensional map. And those X can be defined as apples and bananas and money. So basically, dimensions are just, in some sense, how many numbers do I need to define that state of the system currently? And when we are talking about, when we went to module 3 here, this particular item is just telling us we need 6 numbers, or whatever these things are, probably numbers only, which tell us everything we need to know about that state in that time. If you all have any questions here, I know it wasn't as clear as it should be, but dimensions basically just mean how much information. So like, look at this for example. If this is the data set that we have, the dimensions will be the columns, right? Like in order to know about one particular item, I need 1, 2, 3, 4, 5, 6, 7, 8, 8 sets of information. So it's an 8-dimensional data set. Okay. So that's what we are talking about when we are talking about dimensions. Obviously, it's a deeper topic, but we don't need to understand more than that. Like that's pretty much it. And sometimes these things can be called vectors too. And we can get into why that is when we go towards like the calculus side of the this lecture. Another thing that Stella found, which was a little mathy, were like these graphs, where you look at, like to find the slope of a line was what the goal of this
Rohan.
section. Yeah.
Wait, slow down. Okay, so that was one section, right? Does anyone have any questions about the real vector? Is this like in any capacity unclear as of right now?
All right. I guess I didn't cover also the fact that there are different kinds of numbers. So like, if we go here, this is where I'd like just added this, where like the real numbers, the irrational numbers, rational numbers, fractions we know, integers are like 1, 2, 3, 4, 5. There could be negative and like positive integers. Positive integers are basically called whole numbers. Whole numbers include 0 and the natural numbers. Natural numbers are 1 onwards, so 1, 2, 3, 4. So whole numbers are 0, 1, 2, 3, 4, everything that comes in the set. Then negative integers and all of these whole numbers combined become integers. Integers and fractions make rational numbers. Again, for us, for the most part, we don't need to care about rational and irrational. The point is any number that you'll ever encounter, including pi or like, the number e or like any special numbers also, they all will be real numbers for us. And when you write it in this format, where did it go? This basically means that this is a vector which is the element of real numbers of dimension 6.
Yeah.
Yeah. Someone wrote, I've been trying to catch the sessions live. CryptoKeeper.
Oh, by CryptoKeeper. Oh, you're all good. I'm sorry. This is colliding now. Everyone pushed me to shift this to a little bit later in the day, and well, I'm sorry.
I know.
But yeah, I think we're good. If you have any more questions, don't feel like like you cannot ask about it, right?
Yeah. And what I'll do is go through some of the white papers that I can and keep on adding the math like symbols that I know, that I see. And we can try to make a repository of all the math symbols so we don't get confused when we're looking at it. Okay, so here basically, in order to find, if you look at a line, right, any straight line, at the end of the day, you just need 2 points to define the straight line. Like if I point here and point here, I can draw a straight line between it. And the point is that any 2 points can create a straight line for us. So when we are given 2 points on a coordinate plane, we can draw a line against it and it'll have a slope. And this is the way you find the slope. Give me a sec. Yeah. Which is basically change in y divided by the change in x is what you need to do. So I'll take the y coordinate of the first point, subtract it with the y coordinate of the second point, divided by x coordinate of the first point, and subtracting it from the x coordinate of the second point. So you would get 20 minus 8 upon 10 minus 25, and you get 0.8. So basically, again, like change in y upon change in x is the definition of a slope. And slopes, again, start becoming quite important for us. Not only when we're talking about constant sum market makers that we were going through, but also when we are looking at constant product market makers or any kind of bonding curves, right? Like any curve that you have, which is on which the state of a system is defined. You need to find the slope of it, because the slope has a real world definition, and we can get to what it means later. I mean, in this case, we can talk about the slope of this, the slope itself will mean the price of the item. Is this where they're, yeah, same price, yeah. Since the slope is constant, we have the same price across wherever we are. If we are out here on the curve or if we are out here on the curve, the price of y divided by x will always be the same. Because in order to get delta y out of the system, like delta y by delta x will always be constant because the slope is constant because it's one straight line. Is this clear to us? I mean, for example, like I can show you another graph. Out here. So let's say we are driving a car. Yeah. Let's say this is the system, right? In the sense that what we're trying to model is a car which is going from point A to point B, and it has different speeds at different points in the journey. All right. We can map it like this. Like for example, what we're doing is turning the car up. Wait, am I going full screen? Yeah. Right? This is the distance that it covered, and this is the time it took to cover it. Okay. Basically, if we look at the graph itself, I hope you can see this is visible, right? Yeah.
Yes.
So, in this case, the slope of the line will have a real world definition too, because what it will mean is how much distance, like how much of y changes when I change x. That's the question we're asking when we're finding the slope. And change in distance upon change in time is speed. So the slope of a curve which has distance upon time is basically speed or velocity or whatever you want. Like in this case, yeah, these are, if you're trying to find the slope in this area of the graph, you get the speed at this point. And this is in some sense what a speedometer does, right? Like if you're in a car and you're driving and it says, hey, you're driving at 30 kilometers per hour. The point is that if you really think about it, it kind of doesn't make sense. Like in the sense that how can you say that I'm driving at 30 kilometers per hour at this point of time? Simply because speed is defined by how much distance you have covered in how much time. So if I ask you in the moment of time, what's your speed? How would you even go about answering that question? Because that moment of time is zero, like delta t is zero, right? Like it's the time at that point, time isn't changing because that's the definition of a moment. So you're not covering any distance at that point of time because it's a snapshot of the picture. So the motion isn't moving. But the way we go about answering it in some senses, if we were to move a little further, if we let time go a little bit more, how much distance would have been covered in that much time? And that's basically how we go about answering all these questions, because rate of changes are very hard to define in specific moments. But what we can do is make the moment smaller and smaller and just assume that if the tiniest moment was to pass, how much distance would have been covered? And that basically we've got into what a derivative is, and this is the definition of a derivative. We can go about it here. I mean, we're looking at change in distance and change in time, and if you make the change in time smaller and smaller and smaller, the amount of distance will get smaller too. But whatever number that we approach towards is the actual slope at that curve. And you can see that, like, he gives that speedometer definition too. This is a brilliant article to go through, by the way. It's a very good, and there are a bunch of sets of videos for this. Yeah, so this is the example, right? The closer we get, right, to smaller and smaller time, it kind of is the slope at that point. Like we're looking at the slope of the curve at that point. And when curves get curvier and like more confusing, it's always easier to just look at slopes at particular points. And the way you do it is through calculus. The way you do it is through finding the derivative of the slope at that point, which is basically just ds by dt. ds meaning a small change in like the height and small change in time. Like the y variable and the x variable. So what we need to get from all of that is that curves can get more and more confusing over time, like for example like this. But in order to find the slope, all you need to do is take a point very close to it, and then divide it by the amount of y that you moved and the amount of x that you moved. That basically will get you the slope of the curve at that point. If we want to find the derivative, yeah.
Can we talk about something that I wasn't aware of.
Yeah.
Is in the next slide where we're talking about the constant product. I saw this only as a curve, right? But then you taught me that this is in fact two cones or a cone being cut in half.
Yeah.
Yeah. And so I'm just wondering, out of curiosity, maybe you can send some emoji reactions. Did all of you know this was a 3D item that is being cut?
I mean, it depends. Okay, so I'm sure. Yeah.
Good. Okay. It's not just me. Okay.
No, of course, yeah, of course.
Can I show the
And also,
Blender thing?
yeah,
that you
please.
did?
Please
Yeah?
do.
Okay.
Should I stop?
No, we know it.
You knew it? Kojak? You knew it? Okay, that's fair, I guess. Okay, so anyhow, for me to understand this better, we actually did this little Blender animation yesterday. And this is what this is, right? And if you look at this, these are like two cones. So if you graph this formula of a constant product automated market maker in Desmos, I hope you guys have started to use Desmos because it's such a good tool. This is actually it, and I mean, it kind of surprised me a lot, to be honest. I only saw it as like a two-dimensional.
Let me give some context.
Yeah. Okay.
Basically, there are a bunch of curves. Like, so the curve that we are mapping when we map xy equal to k, it's called a cone. It's called a hyperbola, and hyperbolas. There's parabolas and ellipses and circles, right? So if you imagine two cones like this, and if you cut them in different angles, so like, for example, if you cut it flat, the cross section that you'll cut on the cone itself will be a circle, right? If you look at the cone from the top and you cut it, like horizontally. If you cut it at an angle, the cross section. Can we show this actually? This will be really cool.
Sorry, guys. Can you repeat what are you doing these cones? I lost a little bit.
Yeah. So these are two cones.
Okay.
Right? And if we take a plane, can you bring a plane to cut it first? Yeah.
Okay.
Right, so if we move it up, yeah. Yeah, can we look at the cross section? Yeah. So the cross section will basically be an ellipse here. If we put it parallel, it'll be a circle, right? Because the cone is circular.
Yeah.
But if we cut it at an angle, it'll be an ellipse. If we cut it horizontally, you'll get a hyperbola, which was the one we had. And in some other angle that we cut it, we get a parabola. And these are just cuts of double cones, like extended cones, by planes and different angles. And that's when you get these curves. What's really fascinating is these curves also show up in gravity. Like if you throw a ball, it kind of follows the path of a parabola. Like it goes up and then comes down, right? It follows a parabolic path. If you throw it a lot more faster, it'll actually go in orbit and it'll become a circle. A little less will become an ellipse, like because Earth around the sun is an ellipse, right? We circle the sun in an ellipse, and if it's even more, then it becomes hyperbolic because you'll go out of orbit. So these curves show up in a lot of places. We are using one of these curves, and these curves have very fascinating properties. I mean, every curve will have some property. In this case, we'll talk about it. Like the hyperbola has that invariant property of x into y is equal to a constant. And that has, again, very fascinating mathematical implications. Like slippage is much easier to calculate than you would think. Like there are many ways to calculate slippage, but we'll go through it. Are you graphing it? Yeah.
I figured I should.
Just xy is equal to k. Don't put. Okay, this also works. Yeah, I don't know this. Yeah.
And you can tell this is the same thing, right? If you look at this, right?
Is that on Desmos as well?
No, no. That's Blender.
Okay, got it.
How you do this with 3D? Okay, that's different. Okay.
Yeah, it's
Different
that's
software,
Blender.
right?
software. But here you can tell better what we're trying to show, right? That this is not just a two-dimensional line in a sense, it actually is a cross-section of a 3D solid. And I just thought for like my personal understanding, it really helped to understand that part. Because I looked at that just as a line, as a curve, right? I didn't look at this as a cross-section.
Yeah. And also, like, if you look at when you're changing k, in some sense, what you're changing is where you're cutting the cone from. So if k is equal to 0, right, it's cutting the cone exactly in half. Yeah. And we can show it in that graph also. It'll become just exactly 90 degrees cut.
Oh.
It becomes the graph itself, yeah.
I cannot show it here because that's the best I can do about it. It's the same.
It's basically the x and y axis. Yeah.
Yeah.
So yeah, and if we keep on adding k, like when we are changing k, it's basically moving the cut a little further from the center. But anyway, this is just a random detour that we took.
Fun realization.
Yeah.
Okay, I'm stopping now. I'm being confusing.
I'm sharing my screen again. But yeah, I mean, if you know that, right, you can actually look into the properties of the hyperbola and actually find properties that you'd want in your market maker, and maybe that curve will solve that issue for you. In some sense, like what happens here is we are bounding the state of the system, like the state being the x and y tokens, the way they will be they're tied together, right? Like in the sense that they now aren't allowed to go here. They're not allowed to go anywhere else on the state space. They are bounded to this curve, which is why we probably call it bonded curves. Like we're binding the variables to a certain curve that we choose. And when we make the k invariant, we are basically fixing what the bonded curve will be. That's when like the properties of, like this was also a section in module 3 where they were discussing basically how to find the slope of a curve at a point. So I mean, like, and this is the definition of it, which is again limit delta x tends to 0. The way you should read this always is what this means is delta x is tending towards the 0, which means we are making the so when you're looking at a curve and you're trying to find the slope, you'll take two different points on the curve. And let me show you maybe like F11 and out here. Yeah. So let's say this is the bonding curve that we have, right? So I'll take this point and I'll take this point and I'll draw a line through it. This could be the slope, but we can do a better, like this line itself could be the slope, but we can do better. We can take points closer and closer and closer and closer and closer and closer until we get to this point where we want to find the slope itself.
Yeah.
And we can take a tiny infinitesimal step on the curve in this direction, and then do the same thing as taking this point, subtracting the y's, dividing by the subtracting the x's, and that's the slope definition that we had, which is basically what calculus is. You're actually just finding the slope at a point. But the point is, it just happens to be that we are getting closer and closer, almost close to 0. Like the delta x is as close to 0 as you can be, which is infinitesimally small. Then you get the slope at a point. And that is what we're doing. Again, no need to know all of this. The way you actually, if you have a curve and you want to find the slope, you just go to Wolfram Alpha and you type out this thing, derivative of, try to put y on one side of the equation. So y is equal to k by x, right? So we can take a random k, 10 by x. This is the same curve, right? xy is equal to 10 is the same as y is equal to 10 by x. Are people clear with that? Like, so if you put y on one side, you basically get a correct derivative, which is minus 10 by x squared. So if I want to find the slope of any curve at any point, I open Wolfram alpha. I write the derivative of y is equal to 10 by x or slope. I'm sure slope.
I think it's it's the derivative of the tangent.
Yeah, derivative is the tangent. Yeah.
Yeah. Can I share just a personal reflection?
Yeah.
On everything. So, thank you for going back and going over this. I think it's really important, and an important reflection that I would like to share is that going back over this, I had done in my previous life a lot of calculus and math, and what I had an aha moment because I started to realize is that the diagram in front of you in Desmos, right, the hyperbole, the line. That essentially what calculus is telling us, and when we model these tokens, like with the formula, is that how do they react at a certain point of time in a controlled environment? And when we know that sort of slope, we know at what is our maximum exposure to the positive and to the negative. And I thought that was really cool when you step back and you think about it from a token engineering perspective. It was a different way to apply and understand calculus and how you can determine that rate of change of that sort of underlying token in relation to the constant, the curve in which it's at, which I think is really cool. I think it's a really cool thing to understand.
Yeah. No, I agree, and it's very important to understand too, simply because, for example, if you want to calculate slippage on any of these curves, right? It becomes essential to understand what is actually happening. Like if I'm at this point, which is, let's say x is equal to 2, and I'm going to this point, for example, if I'm at 1, 12, and I get to 12, 1, which means I traded 11 tokens of x to get 11 tokens of y, let's say. Why is it that's what happened? Because I was expecting to get a lot more. And I can show you on the curve what's actually happening, like what slippage actually means, what spot price actually means. Spot price, by the way, is the slope at the curve. Because at this point, the slope of the curve is minus 12. This is, by the way, the price. So minus 12 meaning 12. I expect that for every trade of x, like for 1x, I should get 12 y's, is what I'm expecting when I'm here. But when I actually do 1x, I actually just get around 6, because the difference between here and here was, wait, let me just add this point, k by x, right? It's 6. Sorry, k by x 1. Okay, anyway, I'll have to do this manually. But from 12, y became 6. And 6 was the difference of y, and 1 was the difference of x. So I actually just got 6 tokens out for my first X token that I traded. Which means the effective price was 6, not 12. And the rest was slippage. Now it's a question as to why this happens. Let's go through the slides, and I think I'll get to the interaction part later. But that's what we need to answer through all of these things that we're learning in math. But again, what you need to remember right now is the slope at every point is the spot price that we have. Simply because the graph that we are graphing is y by x, and y is token y, x is token x. So change in token y per token x is the price. Yeah. If we have a constant some market maker, you could decide you could decide a curve which has a higher slope or a lesser slope simply by changing the weights on x and y. And that just comes from y is equal to mx plus c, which is is a straight line. Are straight lines clear to everyone, like the formulae and stuff? If we can do it here, maybe. Right, so y is equal to mx plus c. This is how I had learned it, where m is the slope and c is the intersect as to where it will intercept the x-axis or the y-axis. But yeah. So if this makes sense to everyone, I guess we'll understand weighted constant sum market makers, where basically at every point in this curve, x will be twice as worth as y is. So for every x, you'll have a fixed number of y's that you'll get. Right. I mean, so we get to constant product market makers. Did you have any particular questions here, Stella?
No.
Stella, yeah.
I think
Okay.
that was the point I wanted to actually show the Desmos thingy, but you already did that, so I think we're all good. Unless anyone in here feels like is not going so well, which is totally fair. Again, just want to make sure.
Yeah. So yeah, this chart was pretty interesting too. I mean, like these definitions, like the way the constant product that we have defined, right, where x y is equal to k. In some sense, what we are saying is, like, I mean, because the price of the curve happens to be y by x. So how can I show this? When we looked at the derivative, right? This was k. Can I write this somewhere? Yeah, okay. I'll do this. Okay. I'm going to write this somewhere. Y. So we had xy is equal to k, right? Which basically means that and the derivative that we found was y is equal to minus k by x square, which basically for us, this is not showing properly. Yeah. So basically, what we can do here, is this visible to anyone? Is there a math like typing tool online that I don't know of? Should I just do it here then?
I guess you can do it there. I think that would be
Yeah.
much better.
I just do this. Yeah, that's a good idea.
Yeah.
Yeah.
So I'm just saying, yeah, I think you should just do it in Desmos if you can. I think it'd be easier.
Yeah, I've not used Desmos that much. That's the okay. So y is equal to kx. What I want to do is, I know that the slope of the curve, like dy by dx is equal to minus k by x square. And we know that k itself, right? We know that k is xy. Does that make sense? K is xy. So I can always substitute k for xy.
Yeah.
And when x and x can get cancelled, if that also makes sense, then we can like divide these two. And what we end up getting is dy by dx, which is the price of y for the price of x, like the ratio, is always minus y by x, which is the what do you say, property of this curve itself, which is that the slope of the curve is always defined by y by x, which basically means that if you just know the amount of y and the amount of x in the system, that is the slope at the point. So like if you go here, which is why like the slope of the curve will always be y by x, and that is the price. The price of x is y by x and price of y is x by y, which is very interesting. And that's again a property of the curve that we have right now. It's not a true statement for any random curve, but right now xy is equal to k. This thing is what happens. This was the part where I feel like most of our any question, like any kind of problems that you want to solve, or you want to find slippage or effective price, spot price, everything you can do with this. All you need to know. You had a doubt here, right, Stella?
Well, I just haven't done this in a while, so I was pretty confused. But
Okay.
this is actually the point where I would suggest to take a look at the 5-minute video that Octopus recorded, kind of explaining how to solve this, if that
Should I
makes
open it?
sense. Yeah. No, it's a Trojan horse. Don't open it.
Is it audible?
Yeah, it's audible. It should be. But I can. It's not. Can you hear? Can you hear it from your side?
No,
Oh,
Because
what about now?
Because I can't.
I can't hear the video. I can hear you clearly
Oh.
speaking, but not.
Now?
No, I cannot hear it either. So maybe we have to look at this in our own time. But the point is that I think the most confusing part to me is like, how can he bring the... Oh, wait. Can you go back to the... Sorry, can you go back to the presentation, Roro? Ah. Okay, so for me, I think the most confusing part is how he even came to the second line, right? X plus delta x times y plus delta y equals xy. And the reason is that I didn't really understand the first line, which essentially says the same thing, right? It's like the old xy is equals to the constant because it's a constant to the new xy. And I didn't understand that part, and this is why I couldn't even go beyond the first two lines. But yeah, maybe you can try and re-explain this because the video was not edited well. Andrew, shout out to you, man. You need to learn video editing. Rohan, you're on mute.
No, I was saying I could hear it. Maybe I'm not sharing it right, but I could hear the video. But anyway, okay, so you're confused. Basically, let's say we are here, right? We are at this state where, or let's just start at the state 1, 12, which is x. The amount of token x is 1, and the amount of token y is 12. And we move to the state where amount of token x is 6, and the amount of token y is 2. Is there a way for me to get the label itself of state? Can I get the number? Yeah, okay, perfect. Yeah. So we went from x being 1 to x being 2, and y being 12 to y being 6, right? So when we say x old, y old, what we are doing is x old is 1 and y old is 12. X new is 2 and y new is 2. In fact, we can just go here and like actually do a question together, which will make a lot of sense for everyone. This is a question that was there in one of the what do you say, the module exams that we had. But basically, Stella, do you want to go through, like, do you want to read this and actually tell me, like, what all information do you actually have from the question itself?
Putting me
What
on
is
the
x?
spot. Okay,
Yeah,
fine.
yeah.
So x times y gleich k equals k, sorry, gleich k equals k is the constant product, right? So whatever k says is the same as what x times y says.
Yeah, correct.
Okay. Did we lose Artem on this? He's like, oh, fuck that
Yeah,
shit.
no, he said he had to go. Yeah.
Okay, that's fine.
Yeah.
Okay. Okay. X represents the amount of token X and Y represents the amount of token Y. Initially, there are 3 token X and 300 token Y. Alice comes and makes a trade that increases the number of token Y in the pool by 200. How much token X does she receive in exchange? There are no fees in this pool. Okay, that makes stuff a little bit easier,
Okay.
I guess.
So this is what mathematically.
Yeah.
This is how I go about solving problems, right? I first write a statement of what all is given to us. Like, what all do we know about the system? We know that x into y is equal to k, right?
Yeah.
We know that x old or x1, I call it x1.
Yeah.
x1 is equal to 3 and y1 is equal to 300, right? That's what they say.
Yeah.
There were 3 token x's and 300 token y's, right? So
Yeah.
both of these informations we know. And we also know this another thing. Wait, let me add this. Oh, this is an image, okay. That y2, like, we are going from x1, y1 to x2, y2. That's the next point. Like, we are having a state transition from x1, y1 to x2, y2 after the trade. So y2 is y1 plus 200 is what is told to us.
So 500?
Does that make sense? Yeah. But the point is, like, the way we define y2 is x1 here. is y, like y, whatever y was there plus the delta y that's changing. So y2, like y new, will by definite, like we are just defining it as y old plus delta y, right? Like it's just a way to write that whatever the old was plus whatever change has happened. Is that not clear? Like,
well, the concept, I guess, is clear, but it's also very clear what Stella is going to study during our 3 weeks of break. A lot of calculus.
no, what Lutra is saying also, yeah, so new value is equal to old value plus the change. And
instead, sorry, Roro. Maybe it's just this kind of delta which is confusing. Delta is just an abstract for the change. Since we, in our example, it's 200, but we want to have it in a more general formulation. And maybe another one comes in and just wants to trade 50. So we write the old value of y and then the change that happens to y. In this concrete example, it will be 200, but it may be in another example 5. So that's the reason why we simply write the change or the delta of y.
Yeah, I know the number. Got you. Okay.
Yeah, so no, that's exactly right. Like y2 will always. Starter, do you have something to say?
No, I was just gonna try to say something, then I paused. You know what helped me, Stella, was I actually took the equation. I started back. Rohan, can you go back to the full breakdown of that equation? The proof that they had. Yeah. And you know what you could do here, right? And I because back in the day, my TA days, when you'd do this with somebody, I would start for the very first equation and maybe have somebody who remembers the math beside you and get them to walk through and you do the arithmetic and the solution step by step. That way you'll see the mechanics of how you're doing the proof of the equation. And when you do that, you you'll have a better understanding of what each aspect. That's how I approached it. When I refreshed my memory, it allowed me to remember, oh, okay, this is how it works, this is what it was. I don't know, I think maybe that might help a little bit.
Yeah, no, it did when Octopus explained it to me, but now that I look at it again, it looks again like very gibberishy. I'm so sorry, guys. I'm so sorry. I'm not good with that. I haven't touched this in like forever, and I'm aware I just need to relearn all of this, I think.
I mean, so these are the equations we can like start with. Where's my delta? Delta x.
Okay, I get delta x though, right? It's just the change that happens to x, like to x1
right.
Essentially. So
yeah,
I get that part, right?
These are all the equations we have, and this solves the problem for us. Where like basically, what is given to us? Like xy is equal to k. X1 was 3, y1 was 300. X2 is y1 plus 200. Right. This is all the information that we had, and another information that we have is x2 is x1 plus delta. Okay. Or x1 minus delta x, whatever we want to define, both work. I can cancel this. I've defined it down. Oops. Yeah. Right. So first I write what all is given to us. Then I write what all we need to find, which is how much token X does she receive. So if X2 is we can define this way. And this basically is just a substitution. Like I'm struggling to actually how to go about this. But the way you solve any of these equations is you put x1, y1 is equal to k, because that is always going to be true. And x2, y2 is equal to k is also always going to be true. Does that make sense? Because we are always on this curve, right? So x1 and y1 multiplied together will always be a constant, and x2 and y2 will always be a constant too. Yeah. And that's what is happening here, right? This is what the statement is saying, that k will always be defined as the multiplication of x's and y's at the point. And yeah, do we want to solve this? Do you want to go line by line and do it? Like, I don't know what will help here. Like that's why.
Uh,
And also what will help for others too.
a good question. I think Lutra understands this very well. Hibiscus cultivar understands this very well, and Kojak probably as well. So I guess I'm on my own in this one, and that's
So,
fine. You know,
okay.
I think.
Then maybe we can do this after the session if nobody else
No,
wants to go
I
through.
just really think I need to study this from scratch. I don't really have a choice, Rohan. I haven't touched calculus in years, and now I have to do it in English.
Right. No, this is yeah. I get it. Yeah.
What might help is maybe really start with the first line of the equation, right?
Yeah, I get that one. That's the specific amazing part about a constant, right? So be it the new one or the old one, it's gonna be a constant because it's always built up on the slope, right? Isn't that the thing?
Yeah.
So I understand that part. Then you have okay, let me try. Okay. Then you have token X plus the new token X, which we don't know the number of, but there will be a change. Then you multiply that by token Y, right? The amount of token Y and the change that happens then ultimately to token Y, because if token X changes, token Y changes because it's a constant. That is being reflected in X times Y because X times Y is the constant, right? So we could also write K here. It wouldn't need to say X, Y,
exactly.
right? Okay.
Perfect. Yeah.
Cool.
No, but what I would add is in our question, right? We know that X was 3.
Yeah.
Right? And Y was 300.
300. Yeah.
And Alice changed the amount of Y in the system by 200 is what is told to us, right?
Yeah.
So delta Y will be that amount, 200. So this amount, which is Y new, these two are the same thing, will be 200 plus 300, right?
Yeah.
So we'll have 500 into whatever. Like, so now we can go through all of this, or we can just literally solve it here itself, right?
Okay.
Like I can actually do it on text in front of you.
Actually,
where if you have,
can we do this a little bit differently? Can we do this?
Okay.
Okay, because I think I might now understand what's my issue in the first place. Because I cannot remember everything that you can remember, right? I have like real issues with that. So if we go in here, right? And then I'm just taking out my little pencil. And then I'm just gonna write the numbers underneath.
Yeah.
So can you tell me again what was what?
So X, by the way, the first bracket itself, right?
Yeah.
That is the entire bracket is X new.
This is X new, and this is Y new, right?
Correct. Yeah.
Because it's the old state added to the new state.
Yeah, correct.
This is Y, right? Okay, cool.
So if you go up, it's the same equation. We literally wrote X new into Y new is equal to X old into Y old. And in this case, X old and Y old are like X and Y itself. So in the question, we had X is equal to 3 and Y is equal to 300. So X, 3. And this is 300.
Okay.
And delta Y we knew was, you can read the question if you,
200.
200, right?
Yeah, perfect. Yeah. So now we don't know what delta X is. And that's the goal.
Yeah. Oh my god, this is helping so much. Okay.
Yeah.
I'm so sorry.
And this is XY we know. XY we know, so we can put that too.
Oh, we know the old one, you're right. Well, so
303.
303, yeah.
So we can just do 300 into 3. Yeah. No, 300 and 3. Like, I mean, 300 into 3.
300
Sorry.
times 3. Yeah, you're right. I'm sorry.
Yeah. Right, yeah.
Yeah.
It's a multiplication, yeah. And screw all of the rest of the stuff. We can actually just solve this equation that we have. So we have 900, which is equal to K. like on the right side, right? 300 into 3 will be 900. Y new will be 500. Correct?
Yeah. And then we have.
And 3 plus delta x, we don't know what to do about it right now.
Yeah. This is the current.
So so the way we go about solving it is we can like take it to the right or something because it's getting crowded.
Well, wait.
You can actually just move the image, no? Maybe no, yeah, maybe not.
I can do this and then just delete everything. Sorry.
No, but when you see that equation, right, at the end,
yeah. What?
You can clearly tell that the delta x ka value will be found because I can do 900 by 500 now. I can take 500 on the other side by dividing both the equations by 500. Does that make sense? Divide both the equations by 500.
I don't even know why you can take it over to the other side. That's my whole problem right now. I know there used to be a thing. I'm not sure if this is Lutra might know because he studied math in Germany. Was it something like this, and then you would be just saying 500? Is that what you used to do in Germany? I don't really remember.
It's a long time ago. But yes, if you want to divide 500 from the left-hand side to the right-hand side, you would write it like this minus 500.
So minus 500?
No, that's subtraction. So whatever you do on the left, you'll have to do on the right, right? Because
how do you visually do this? You write just times.
No, just draw a line under 900 and divide it, like put 500. Like, you know, the division line and then 500. Is that not how you write it? And then left side also you'll have to do the same. Because if you do something on the right, you have to do on the
This is when this cancels itself out, right? And
Perfect.
900. Wait, what? I can barely hear you, Lutra. Sorry.
Mind.
What?
Yeah, even I continue.
I just said don't mind.
Aw, thank you.
It's
Thank
some
you guys for
audio
being
problem?
so patient. But this is I'm annoying myself right now. I'm sorry. Okay.
No, and you're done. Now, basically on the left side, we have delta x plus 3. 3 plus delta x, right? And on the right, we have whatever, 9 by 5. 9 divided by 5. And now you can just subtract both sides by 3. Minus 3 on both sides.
Like this?
No, so what will happen here is you want to do minus 3. Not plus, so you write 3 plus delta x and then do minus 3. And then minus 3. Yeah, perfect. And 9 by 5 minus 3. Do you understand why we are doing it? Like, what we are basically doing is somehow removing all the things on the left, one by one.
Mm-hmm. Okay.
So 3 minus 3 will cut off and you'll just get delta x on this side. Which will be equal to 9 by 5 minus 3. And you can use a calculator to find this. Doesn't matter. It's 1.8
Thank you guys
minus
for doing
3.
This.
1.8 minus 3 is what we need to do.
Okay, fine. But this is... okay, now I get it. Thank you.
Yeah, so we found delta x. We still aren't done though. Right, we found delta x. That's not what we had to find. What was asked is, was delta x what we had to find? What is the question again?
I think in the example
It
that was
was-
given...
Yeah,
How many-
correct. Yeah, we need to find delta x, right, correct.
Yeah, in this one, yes. In the original one, it was delta y.
Yeah. No, but that's not what we were doing, right? We were just finding out for the exam. It doesn't matter whether you use the final formula that is below, or you start from the x nu is equal to x nu into y nu is equal to k. You'll get the same answer. But that's, I mean, this is basically it. Like, all we have to do is plug in the values. Yeah, let's go.
Oh,
Congrats!
Although the minus sign, right? Yeah, the minus sign means that amount of tokens were taken away from the system and given to someone. So that's why we got a minus sign, which is good. Yeah.
My nerves.
Let's go.
My nerves are shattered. Okay, fine. No, but this is what I mean, right? I haven't done this in 20 years, and I just need to do a bunch of exercises. I think there is not really a way around it, but I really appreciate all of your patience of running me through this equation.
Yeah. No, and it's basically, I mean, algebra is something you just have to, in this case, get used to. Or you can just straight up use the formula that are given. You could do that. Like, you could just take the final formula and just plug values that we know. So in case of, by the way, like when we look at xy is equal to k, right? It's a symmetric equation, right? So in some sense, when you have a formula that's showing you what delta y is, if you change all the x's to y's in the formula, you get what delta x is.
Yeah.
But again, like that's too complicated maybe. But
No, it's just it's vice versa, and it's just like the variables then instead of numbers.
Yeah.
I'm telling you, I understand the concept, right?
Mm-hmm.
But the concept doesn't help me to actually solve an equation, does it? You know, it's like, oh yeah, I understand, but I'm also really good at, hey, I don't know how to solve this by myself. So
what I'm wondering,
this is
does this-
exercising, I think, isn't it?
yeah, I mean, it is basically.
Yeah. So
I'm wondering this. Can we do this?
my Christmas holidays. Woohoo!
Solve. We can actually solve.
Wait, what?
What was it? I'm actually trying to solve on Wolfram Alpha. We had the equation, right? We had 3 plus whatever we can call it x, for example,
Yeah.
into 500 is equal to 900, right?
Yeah.
This is what we had.
Yeah.
I think if we just put it here, we get the answer. X is equal to minus 6 by 5, right? 1.2, yeah. So actually, again, like even all of these questions, in fact, if you open step by step, it'll tell you every step, like,
This is
Oh,
gonna be
me.
so helpful.
Cool.
Yeah.
yeah. So see, divide both sides by 500, then subtract 3, they're gonna do next, but we have to go pro for that.
Maybe we should ask for a pro account for token engineer.
The student pricing, yeah.
For the non-mathematicians under us.
Yeah.
Yeah.
By the way, this program is damn cool. Like you can say height of Eiffel Tower, right?
Yeah.
Wait, what the Eiffel Tower divided by distance to the moon.
What the
And it'll give
hell?
you yeah, this thing.
That's a crazy ask, though. Oh, actually,
Yeah.
can you go back to the presentation?
Yeah.
For the people who are not attending this session? Yeah, because so wait, yeah, quest homework. Okay, fine. For next time, right? It's the last 4 sections of module 3. So agent actions part 2, performance indicators, introducing fees, conclusion and further development. And of course, chat in the Discord and check the Notion for prior recordings and Roro's amazing summaries. And then next slide, which I think is super useful, is all the tools we've been using in here except for Blender, because, you know, I play around in Blender because it's something that I understand very well, but that might not be helpful to everyone. And there is the Wolfram Alpha website link. There is a multivariable calculus online course, active calculus, and also a really cool YouTube channel that Roro recommended that helped me a lot understanding some concepts is 3 Blue 1 Brown.
Oops.
Exactly.
Yeah.
So
Yeah. This is my they have like an entire calculus playlist, and it's extremely visual, like extremely visual. Everything is animated, everything grows. It's beautiful. But yeah, in fact, my biggest recommendation. They also have a blog series, the one I showed you.
yeah.
So very helpful to refresh any memories. In fact, it adds so much to your knowledge of calculus. Yeah.
Now, so for me, it's super helpful. And then the other, wait, go back. You're way too
Oh,
fast.
oops.
Two. And
Sorry,
then
sorry.
one thing that I wanted to specifically underline is if math is no fun to you, right? Matt Parker will make sure it is going to be fun for you. So
Yes,
I
kind of
actually
fun.
think I'm struggling with this. I'm not gonna lie, right? But it's still fun for me, and it's like a challenge I want to take up. But I realize that's probably not the same for everyone. So in case you need some like additional motivation for finding math cool and fun, give a look at Matt Parker's stand-up math YouTube channel. It will do the trick, I promise. It's stand-up comedy combined with a vast knowledge, not only about math. Yeah. Okay, I'm
Yeah,
done. I'm
even
done.
a lot of computer science topics. I remember they were playing around with some topic, and like they were like, hey, how fast can we solve this equation? And they like had this whole tournament where everybody who was watching that video also contributed in their codes, and it was a like race to like who can do it the fastest, and like they solved a equation 1 billion times faster than what Matt Parker had solved initially. And it was like a whole like tournament, and it was really fun. So he has a cool community of people that do stuff together. Yeah. And Luta, for you, I think this thing, 3 Blue 1 Brown, is an amazing resource. Like you will fall in love with math all over again because you know enough to actually remember certain things, and he goes from the basics to explain how calculus was invented, makes you want to invent it, and just beautiful. Like, yeah.
Sounds really great to me. So really, thank you so much for all your efforts and the material. And well, it's such a fun, to get engaged and to check out all these new tools. And that's thanks to you.
Thank you.
You're on mute.
Oh yeah.
Oops, sorry. I found a really cool website called MetaMD, MetaSD, I think. Wait,
No, MetaMD, I think you're right. The hack
Meta-
site, right?
no, it is MetaSD. Sorry, no.
Oh.
It has like a bunch of like stock and flow diagrams, like for different kinds of. Again, I'm sorry, I'm sharing again, but this. And what I'm planning to do over the next few months, like these stock and flow diagrams for different systems, like you can look at, for example, climate change, or you can look at this: business, biology, dynamics, economics, engineering, environment. Let's look at environment, right? Health, population, all kinds of things. And you can take one of these diagrams, and my goal is to like do it on CAD. Maybe if someone's interested to do it on machinations, it'll be interesting to actually compare. But the point is, I want to actually build out all of these models and put them out as open source, like things that people can play around with. So, for example, to show how climate change affects. So, this is something I'm planning to do as a side project in the next few months, and I'm planning to put it up as a YouTube series. But yeah, let's see if that actually happens. And I'm saying it here to commit to it.
Now it's
Yeah.
being recorded. You're not getting out of
Yeah.
it. No, but
Yeah.
if you start with something simple, I would want to try and do it on machinations with you.
Yeah, look at this. Like, this is so simple. Like,
Yeah.
wait, let me find something that actually we'll enjoy. It's super fun. Like, environmental homeostasis. Okay, this may be complex, but maybe not. I don't know.
I think-
But we can find something that's easy enough, but also fun enough to want to do.
Yeah.
Like, because there's a bunch of topics like in economics. Like I saw one that was basically they tried to answer the question of how like how when we have like every business has quarter to quarter goals, and how managers who like over optimize for quarter goals will actually end up performing lesser than the ones who have a long term goal in mind, and they found a system to build it out.
Yeah.
And there's a paper that did it, and I was like, oh, that's so cool. Like, imagine being able to build that and actually give it off as a um, thing where you can just change the sliders and actually see the system evolve. It'll be so cool. But yeah, I'm really fascinated by this, and I really want to do this now. So yeah, if someone wants to come and join with me to build this stuff, it'll be or just give me some kind of point me to interesting systems that I can code up. Yeah.
No, I think that's a good idea.
Pretty cool idea.
Yeah. We're looking right now in machinations for ideas, to model. And Rishi from Jarvis Labs, he was saying that maybe we should focus on modeling things that went wrong to understand the patterns of why these systems go wrong. So, for example, Terra Luna, right? For example, STEP, for example, XE, like all of these things. And I think that's a good idea. The problem is that they are already like kind of very complex in itself. So this is why, like I think it would be good to model things that are first a little bit more relatable. And, I get if, now in machinations, like there are people who have crazy backgrounds, like, computer science and everything. So for them, it's like, what are you talking about? Like, we can do this overnight. It's no problem. And so I want to find a way to approach this, because I cannot do this full time, none of this, right? So my time is also limited. And I think like mapping out problems that are less abstract would probably help me to do that. Yeah, so.
By the way, there is this machinations group starting right now. I think I already registered, but when will it start?
I think it started yesterday.
Okay. Is there a video from the session yesterday?
Yeah, so here's the thing. We don't record that session because sometimes people share confidential information in the study group, which is really nice to learn from. But also, I cannot record it because then it gets published.
But
this is why, this is why it's not being recorded.
Lutra, the Machination has its own YouTube series. They do great explanations. You can go through them.
Oh, okay.
Yeah.
Also, there is, even for Machinations, we have a Notion page, right? And I put this yesterday, I believe, also in the Machinations channel. But here it is again, right, on our side chat. This is where you can see some of the sessions that I recorded in the beginning until, the cool stuff happened that wasn't supposed to be recorded. So there are 8 sessions that are being recorded. In one of them, there's actually a guy from Machinations coming, and he explains like all the different elements, all the little different nodes that you can use and what they do. And also here are some videos that we recommend to have a go through. But yeah, I did all of these, so now I need to, eventually start figuring out how to model my own shit. Yeah.
Their documents are really, really good. Like
they are.
Their getting started page is just amazing. So if you want to get started, Lutra, like just open like their website. It's beautifully like the guided tutorials through everything.
Also,
okay, great, thank you.
Also, there are templates. So you can look at templates. You can look at what the community has done, right? So if you, for example, look in the community builds for Axie Infinity, there's like the whole thing already mapped out, right? Yeah, I mean, you cannot say for sure if if this is, the right version, right? Because it has not been checked or anything, validated. Yeah, exactly. But yeah, I agree with Rohan. They have so many good things on there to take a look at first and get familiar with the tool, and then slowly you can start building your own things. on there. Yeah.
Yeah, let's go. I'll actually share some fun, maybe system modeling stuff, and maybe you guys can pick it up on machinations if y'all are interested too. So then we can actually compare our Python and machination models. That'll be really fun. Yeah.
I have a reflection. I'm not sure whether you guys what you think.
Yeah.
Is the fact that machination feels to me like it's analogous to some kind of a low-code environment. And now, you know, especially hearing what Roro explained last week about coding, you know, how you break it down and then you pass on to the coders. Machination to me feels like a low-code environment, which, you know, with the help of AI, you effectively, you can almost create a sort of a one-man protocol situation where you design it through a low-code environment, whether it's machination or something else, and then the execution will be done by, you know, someone who's well versed in whatever language you want to use, and then boom, you have a protocol. Is that too crazy?
No, I think that's the direction even CAD is taking. So CAD just released like a few days back CAD reference implementation, which is the new version of it. And the goal in some senses, they've coded it in such a way that it could be the backend of a graphical user interface where you can just add blocks, connect to each other, just like machinations. But it gives you the CAD code after, which you can now add your machine learning stuff on it. So in some sense, yeah, like, because the limitation of machination is the fact that once you made the system, you can't test it as rigorously as you could in Python. But if CAD actually goes in this direction and they build it out, you could get that. And I assume, I mean, in theory, machinations is doing everything in some kind of coding language in the back end. So if that also could be given access to, you could do the things we're doing in Python out there too, maybe, who knows.
I mean, we've been bugging them about the fact that it would be nice to, you know, if you're satisfied with your model and you think, you know, you want to get to the next stage, if you could just output Python code from there. Alex couldn't really answer that question. I think we asked Cesar at some point, and he said, like, it's a different language. So that might be difficult.
I see.
But I think, you know, they've been listening a lot to the stuff that we've been asking for and looking for. For example, the new variables function, right? So now you can, if you go to the Machinations YouTube, it's the first video up that's put on Spotlight. It's custom variables. So now you can define your custom variables. That wasn't a thing before, right? And like you will be able to input, for example, ETH price directly or Bitcoin price directly. That wasn't a thing before either. So I think they're working towards that. I would be surprised if they wouldn't, to be honest.
Yeah, no, I'm sure like their backend is obviously not Python, but yeah, I mean, God knows. I don't know how it works.
No idea. But
also, probably they don't want you to do that. They probably want you to stay on the system, right?
They probably do, but
like they want you to keep using the product again and again. Right?
But I think they must be aware
that
their product cannot solve everything.
Yeah, that's true.
So, but then again, Python is open source, so you know, like making a Python integration would be super beneficial to them as well.
Yeah, actually, that is true. Like, because so many people can't code, but you can actually make a machination diagram and pass it on to someone. To do that would be, and it will open up so many more people coming into the system because they know that it could be the pipeline in their companies.
It's a great visual tool.
Yeah, there are other tools like there's Vensim, there's Stellar. Like these are actually tools through which you can graphically model, and you can be way more rigorous. And they have all the statistical libraries involved. Like that's where most of the system dynamics community is. The goal of CAD is to just make it open source.
I mean, I applied to this Python visual scripting tool. I haven't had a chance yet to test it out, but I very well intend to do that during my math studies in the new year. And if I think this is like somewhat, you know, getting into, I will let you guys know. because they sent me.
I'm so jealous. Your Christmas is going to be so much fun.
Isn't it? Oh man, I even gave like everyone in my project, I said like, okay, we're 3 weeks on holidays, and then I said, oh, this is so great, you're gonna be on holidays, and like, oh, I think you're really misunderstanding the meaning of holidays. It just means catching up with a lot of shit that I didn't get to otherwise.
Wait, is this our last session after, like, before the holidays, or we have one more?
No, I think we should have one more on the 16th, no? And then we go into holidays until. Sorry, I'm just making executive decisions here. I think we should be next session. Then after the holidays should be on the 13th, if that is okay.
Okay. Yeah, first then we should do 1 month. So almost a 1 month break.
No, it's 3 weeks. Don't be ridiculous.
I mean, 16th to 13th, right? That sounds like a month. But yeah.
You just want to have 1 more week for the best.
Okay, fine. You
I'm okay with whatever.
You want to do until the 6th?
Yeah, 6th. Again, I don't care. I don't even care in the middle. Like, I like having sessions.
I like having sessions too, but I need to catch up with calculus.
Yeah, that's fine.
And programming, just everything.
Yeah.
No, but okay, let's say next session. Okay, so last session, 16th. Next session in the new year, 6th. Yeah?
Okay, perfect.
Yeah.
Alright.
Yeah. Alright, guys.
Okay.
All right. Thank you both, as always. Much appreciated.
Thank you guys for joining. Yeah.
Yeah, thank you guys.
Thank you so much.
Thank you. See you next week.